Okay, in the previous class, we discussed about what you mean by a metallic conductors and about boundary properties and also some of the boundary conditions. Now we will move on the extension of a boundary where we will be learning if a different means instead of going for a homogeneous medium means here it is going to be a different medium are there within that how our equations are going for how we have to take of those. The next topic is of boundary conditions for perfect dielectric materials. In this case, we will be learning two different ways where our medium what would we be using with a different permittivity. That is, here it is going to be instead of only one permittivity, we will be taking a epsilon 1 and about a permittivity of 2. Okay, this based on different medium. How is the value of the things it's going through in terms of your electric field and also about flux density. Those equations we'll be learning in the today's class. The problem in which there are two different dielectrics, or else about two different dielectrics with different permittivities, and also about a dielectric and also of a conductor. Like in a water, if you are going to pass any of the cable, or in the underground, if you are going to passing any of the material in a vacuum, if you are passing anything, the wire is going to be. In such cases, what is the equations are going to be, and what are all the characteristics of our electric field intensity and also flux density? Those we'll be learning now. This is an example that is taken for the boundary conditions where it is we are going to be applying. Then the condition at the surface of a conductor where we are going to be taking a tangential field are to be 0 in these cases, and one more thing is of the normal electric flux density is going to be equals to the surface charge density on the conductor. These are things we should consider when we are going for the boundary conditions. Now I will be taking the first condition about if it is of two different dielectrics are there. That is I take another first condition. Consider a interface between the two dielectrics having the permittivity epsilon 1 and epsilon 2 and occupying a region 1 and region 2. This is the how it is shown here. This is the region 1 and it is region 2 with a different permittivity, that is about epsilon 1, epsilon 2, and here a small object is placed with a width of delta W and height of delta H, and one more object, circular object here with a small surface area that is delta S, with here it is going to be representing for the electric flux density, and here it is going electric field intensity. Next, the tangential component, we told that it is going to be S0. In the previous cases what we taken, it is the same here also taking, that is integration closed with a closed integration. E dot dl tangential component means E dot dl is going to be equals to 0 based on the conditions what we taken in the theory way. Then around a small closed path on the left of this path, then what is going for of this what he left of this, then E tan 1 into delta W minus, here two different regions are there. First, what is the difference of those? Minus E tan 2 delta W is going to be equals to 0. This is what equation you will be getting. Then a small contribution to the line integral what we are going to be taken by the normal component of electric field intensity E along the section of length delta H. This becomes a, if it is the length height what it is taken of this object, if it is decreased, we are not mentioning that it is of a H, it is where small incremental H, that is delta H is taken. If it is going on decreasing, it's going, if it is going on decreasing, it is near to the region of this what is the line is showing here, right? The same thing here it is written. In such cases there as uh, delta H becomes negligible as delta H is going to be decreasing, the and the closed path. Yes,
Screen is not visible, ma'am.
oh, yeah. Sorry, I didn't share it only. Okay, we'll glance over once. the boundary condition for perfect dielectric material. Here we are going to be taking two different conditions where the, now it is visible.
Yes, ma'am.
Okay, okay. Thank you. Here two different regions it's taken as f-long 1 and f-long 2, and the different examples here taken as two different dielectrics and also dielectric and conductor medium. Then this is an example for us. Then the condition at the surface of the conductor where it is going to be giving a tangential fields should be 0, or it's going to be 0, and a normal electric flux density is equals to the surface charge density on the conductor. This is what the thing. Next we'll be considering of the first case where with the medium what will be taking, it is of a two regions are of a dielectrics having the permittivity f long 1 and f long 2 and occupying the region 1 and region 2. This is the diagram here it is showing a small object with a height of delta h, width of delta w, different electric fields, that is E tan 1 and E tan 2. A region is of region 1 f long 1 and region 2 f long 2 with the permittivities. Then one more circular object is taken here with the area is of delta s surface. Then about flux density dn1, and here it is going to be for across this region it is dn2. Then a tangential components by using of integration, closed integration, E dot dl is going to be equals to 0. Then a small closed path, what it is taken about this one, the whole, that is going to be the equation what will be getting based on this E tan n 1 delta w minus E tan 2 delta w, that is going to be equals to 0. A small contribution to the line integral by the normal component of electric field intensity along the sections of length delta h. This delta h is going on decreasing. When and then if it is going on decreasing, we can neglect of this delta h. In such cases, what the equation is going to be, we will be getting this delta w is going to be equals to 0. Then it is nearly, it's not a 0 actually, it's reaching towards the region. So we can write the equation as E tan n1 by tan 1 is going to be equals to E tan 2. This is the equation what you will be getting. Then this represents a Kirchhoff voltage law where the potential between two nodes is going to be equal, right? V1 is going to be equals to V2. That's what the information it is giving for us. Then the potential difference between any 2 points on the boundary that are separated by a distance of here. Now it's going to be taken in this case in a horizontal fashion. Then separated by a distance delta w is the same immediately above or below the boundary. It may have above or below the boundary what it's taken now. Then if the tangential electric field intensity is a continuous across the boundary, if it is of a continuous one, then a tangential, the flux density is also is going to be a discontinuous. Observe here, tangential electric field intensity is continuous across the boundary, then the tangential of the flux density is going to be a discontinuous, reverse of that. Therefore, tan d tan 1 divided by f long 1 is going to be equals to E tan 1, that is going to be equals to, we told it both are going on to be equal, then E tan 2 is going to be equals to d tan 2 divided by f long 2. Therefore, I can write in terms of flux density, that is d tan 1 divided by d tan 2 is going to be equals to f long 1 divided by f long 2. This you have to remember the equation. This is the boundary condition on the normal components are found just by applying a Gauss law to the small, that is for small this whole box, that is what we call a pill box shown at the right of the figure. This, instead of going for this, we can use of small object like this. Then the sides are again very short. What is the sides are going to be? These sides. Here in this case, for a small object, if I am going to be considering of a small, it's not the whole, it depends on the cable or material what you will be using. A copper wire is very thin, right? It depends on the how you are going to build your construction way. Then a flux leaving the top and the bottom surface is difference. What is leaving, and it is going to be leaving here, and here it is going to be inserting. Therefore the equation, the difference is going to be dn1 with a normal. We are telling now previously we taken in terms of tangential, now it is for the normal case, that is for the flux density. dn1 dot delta s minus of dn2 delta s is going to be equals to delta, how many charges are leaving or entering to the object, that is what q, that is going to be equals to, we know this, the equation is of that q charge, it's going to be equals to the area rho s into of the surface, that is delta s. Therefore we can take write the equation as delta s is, you can neglect of that now, dn1 minus dn2 is going to be equals to rho s. Therefore then assuming the rho area what is going to be covering, it is very negligible, so we can represent that as a zero value only. Therefore rho s is going to be a zero on the interface what it is taken. Then what it is going to be observing here, dn1 is going to be equals to dn2. Therefore that it is indicating for us the normal component of d is of a continuous function. Therefore f long 1 en1 is going to be equals to f long 2 en2. But observe here, in this case it is again reversing, and a normal e is discontinuous. In a tangential it is reverse, again in a normal it is our flux density is continuous but electric field intensity is discontinuous. Don't get confused here, just go on equation, you will be easily, you can bifurcate of those sentences. Then this is one part. Next will be condition, taking one more half part of that. These conditions may be combined to show the change in the vectors, that is how it is going to be varying. We can say of that, that is for flux density and electric field intensity at the surface. Let d1 or else e1 make an angle of theta 1 here. Make an angle of theta 1 with a normal to the surface shown in figure. Here it is going to be a theta 1. Okay, then since a normal component of d are continuous, therefore I can write the equation as dn1 is going to be equals to d1 cos theta, that is nothing but it's going to be equals to d2 cos theta 2 of this angle, then that is going to be equals to dn2. Then the ratio of tangential components are going to be d tan 1 divided by d tan 2 is going to be equals to d1 sin theta 1 divided by d2 sin theta 2, that is nothing but f long 1 divided by f long 2. Then or else I can write the equation as just cross multiplying here, f long 2 d1 sin theta 1 is going to be equals to f long 1 d2 sin theta 2. Then a division of this equation with this, then I will be getting as tan theta 1 divided by tan theta 2 is going to be equals to f long 1 divided by f long 2, you will be getting. Then in figure it has been assumed that what is it is taken in this case, it is assuming that the f long 1, the medium what it is taken, it is of greater than f long 2 and the angle is of theta 1 is greater than theta 2. This is the condition it has to satisfy. Then we can go with the equation of this. Then the direction of electric field intensity on each side of the boundary is going to be identical with the dispersion of our flux density d, because based on the equation that is d is going to be equals to E times L each. Then the magnitude of flux density for the region 2 it's going to be, that is d2 is going to be equals to d1 times square root of cos square theta 1 plus f long 2 divided by f long 1 whole square sin square of theta. Then for the electric field intensity, then E2 is going to be equals to E1 square root of, instead of cos here it is going to be a sin square of theta 1 plus Epsilon 1 divided by epsilon 2 whole square cos square theta. The reverse of this. What's the equation you are taking? From these two equations, it is showing that D is a larger region of the larger permittivity, where unless theta 1 theta 2 should be equals to 0, where the magnitude is of it should not change, unchanged, that's why here taken, and that E is larger in the region of a smaller permittivity, where our angles theta 1 theta 2 should be equals to 90 degree, and here also where its magnitude should not change. These boundary conditions and our magnitude and direction relations are derived from the equations what we taken previously. These will be giving a quick result of any of the boundary we are going to be taken. The condition here is going to be the surface area what it is taken here. Either of the first case what it is taken, what I am going to tell is the what is the surface area of this part, or else the surface area if I am going to be taking when it is of different dielectric mediums are there, due to some after some time intervals there may be a reduction in the size of that wire, or some, due to some reasons it may damage of that, so that even one part it will be for perfect what you are initially you inserted. After some time the other part it may not be similar to the other side in a practical approaches. Whatever the equations we take on now, it is in terms of a theoretical fashion, that both the boundaries are both the surfaces are in a equal and same length it is having, but in a practical approach it is not going to be a same. There will be a slight difference in between of the surfaces, or maybe in terms of height, width, whatever it's going to be changing. That is what here it is taken in the theory part. Then this is what we taken, it is for the one first condition where our it is having only two dielectric medium. Next we will be considering the example where it is having one dielectric medium and about the a conductor. Means in your glass, if you are passing a copper wire, right, the conductor will be copper or aluminum, dielectrics of your glass, what are like these examples are going to be. If it is buried in such ways, what is the equation, what is your field density and what is your flux density in terms of tangential component. Here we will not be talking of the next, move on of that part. The boundary conditions existing at the interface between a conductor and a dielectric are much simpler than what we taken in the previous. Then our flux density and electric field density are both going to be 0 inside the conductor, which is this we know of that. Then and the tangential of E and D field components must both be going to be 0. The same equation what we taken in the previously, that is integration closed integration E dot dl is going to be equals to 0. Then we know that D is going to be epsilon times of E, then applying a Gauss law, then our that taking a closed surface integral. Gauss law means Gaussian surface we are going to be taking here, that closed surface D dot ds is going to be equals to the charge, how much it's going to be passing or passing through that surface, that is equals to q. Then it shows that the both our D, that is flux density, and electric field density are normal to the conductor surface, and dn is going to be equals to rho s, and the en is going to be rho s divided by epsilon. Just remember this, the boundary condition of the what we taken in the previous cases for conductors, free space boundary are going to be valid for conductor and dielectric. The conditions what we taken, the medium what we be choosing, it should be of a free space. Then the boundary, if it is replacing with epsilon not by epsilon, if it is changing instead of free space, if I am going to take some other material, some other medium, then the equation is going to be changing here. The tangential component dt is going to be equals to et is going to be equals to 0. Then dn, that is going to be epsilon times en, that is going to be equals to rho s. Then next we are going to be considering any change that is going to be happening, introducing internally what is going to be within the conducting material that arrives at the surface as a surface charge. Then using of the Ohm's law, we can write the equation as the conductivity, that is J is going to be equals to sigma E. Then the continuity equation we can write here as del dot J is going to be equals to minus rho V divided by dou T, in which the J and rho V are both involved in free charges. Therefore, I can write here as instead of J, I can write del dot sigma E is going to be equals to minus dou rho V divided by dou T, or else I can write the equation here as instead of E, I am going to substitute for instead of flux density, del dot sigma divided by epsilon times of D is going to be equals to minus dou rho V divided by dou T. Then this is one condition. Then assuming that the medium is of a homogeneous, so that sigma and our permittivity is not going to be is not a function of changing, function of positions what it's going for. Then instead of we can remove this part, then equation is remained as del dot D is going to be equals to, just take this side, epsilon divided by sigma dou rho V divided by dou T. By using of the Maxwell's first equation, this is nothing but our volume integral, volume that surface, that is rho V, that is going to be equals to this equation remains as, that is minus sigma epsilon divided by sigma into dou rho V divided by dou T. Then let making an assumption that our conductivity is not a function of rho V, then the simplifying in the equation, then I'll putting as rho V is going to be equals to rho naught e raised to minus sigma divided by epsilon times E. A derivation is there, that derivation is not included for you, no worry of that, just remember the equation, that's enough. Then where rho naught is of a charge density at T is going to be equals to, at T is going to be equals to, this is the charge density. This is going to be taken as exponentially decay of a charge density at every point with the time constant epsilon divided by sigma. This is what the equation telling us. And this time constant we called as a relaxation time. It may be calculated for the relatively poor conductors. The example here it is taken for the distilled water, that is sigma divided by epsilon divided by sigma is the equation. Just to go and substituting the values of this different dielectric values, if you remember, you have to substitute here, then you will be getting for this distilled water is of 3.54 microseconds. This is the relaxation time. Then what is this? It is indicating for us for the distilled water. In 3.54 microseconds, any charge, if we are going to place in the interior of the body of a distilled water, of that distilled water, if I am going to paste any of the wire or any of the material, has dropping about 37% of the initial value. What is it dropping in that it is reducing its charges, that's what initial value. And this rapid decay, that change what it's going to be happening is characteristic of a good conductor. What it's telling, it is of what it is happening, it is indicating that it is of a good conductor, and except for an extremely short transient period, it's not going to be applicable in such application. Then considering a charge density to be 0 with a good conductor, means our charge density should be 0 if I am telling that it is of a good conductor. Then with the physical materials, what it is going to be, with which it is should note that no dielectric material is without a some few electrons. Whatever the dielectric materials it is having, it will be having some of the free electrons. That is one condition. Then all have conductivities different from the 0. It's not that it will be conduction is 0 only. Right? It will be having the conduction, but it's not the value as 0. It may have 0.1, 0.5 or 1. Minimum conductivity is there for the dielectrics. Then the charge introduced internally in any of the any one of them eventually reach the surface, means whatever in a glass if I am going to be taking, it's reaching at the surface of the material. If I'm going to passing a wire at the surface, it will be having some of the few electrons. It's not a comparing with the conductors. Dielectric will be having a few, very, it may be 500 for the conductors, means in your 5 or 10 for your dielectric medium. Like an example I'm giving, take that. This is about a boundary conditions for the perfect dielectrics. This question may ask for dielectric materials for 6 to 8 marks. It depends on the question paper. Okay. Next, we move on to the next topic. That is about the capacitance. We already know about what you mean by capacitor, how it is going to be taking, how the charges are going to be stored in the capacitance. Right? The same thing here is going to be taken. Again, we are learning the same equations, what you already know. Okay. Then next, we'll consider of the capacitance. Considering a two conductors embedded in a homogeneous dielectric, here it is taken as a one medium. This is a medium. Here it is having homogeneous medium. We are telling that. Then it is having two conductors, that is M1 and M2. Here M1 is charged with a negative and M2 is charged with a positive, and the number of charges what it is included for M1 and M2 are equal. That one condition we have to take. If the number of electrons are more for this and the holes are less here, it's not going to be taking like that. The both the charges what it is included, negative charge or as a positive charge for M1 and M2 are equal. Then a conductor M2 carries a total positive charge, that is Q, and M1 carries a equal negative charges, and there is no other charges present in the medium. You should not have that one more positive charge here, one more here. No, you should consider of the two conductors. It should have only of the charges, not any free charges or free electron should be there in that medium. Then, and the total charge of the system is going to be equals to equally positive and equally negative, means total it will be 0 only. Then plus q and minus q, what you will be getting? A 0 only. The charge carried on the surface as a surface charge density, and also that the electric field is normal to the conductor surface. Each conductor is an equipotential surface. What it is taken here is a equipotential surface, that you have to remember. Then since M2 carries a positive charge, the electric flux is directed from what it is going to be, which is charging M2. For that reason, the electric flux what is going to be, it is from positive towards the negative. And M2 is at the more positive potential. In other words, we can tell that the work must be done to carry a positive charge from M1 to M2. When you are going to move a charge, if it is here of a positive charge is there, means a small amount of work has to be done to carry out from this M1 to M2. That is what here it is telling. Next, we'll distinction with our what is going to be the potential difference between M2 and M1 is taken as V0. Potential difference is of, and what is the definition of capacitance? The definition of a capacitance of two conductor system as the ratio of the magnitude of the total charge. Observe here, the ratio of a magnitude of a total charge on either conductor to the magnitude of the potential difference between the conductors. Therefore, the equation is going to be capacitance is going to be charged to the potential, that is V0. In general, determining the charge by the surface integral over a positive conductors and V0 by carrying a unit positive charge from the negative to the positive surface, then the equation is going to be equals to C is going to be equals to integration with surface f long E dot ds divided by minus of integration minus to plus, where it is moving the difference from minus to plus E dot dl. This capacitance is of a, it is telling that it depends on the field. It's not depends on the what is the charge or else what is the voltage difference is applying via. That is capacitance is independent of the potential and the total charge. Based on this equation, we can tell that for their ratio is going to be a constant value only. If the charge density is increased, if it is going to be increased by n times, if a charge density is increased, then Gauss light indicates that the flux density or electric field density is also going to be increased by how much? How much the factor it is increased, that is by n times. As thus the potential difference is going to be. Then what is the capacitance is now? The capacitance is a function of only a physical dimension of a system of conductors and the permittivity of the homogeneous dielectric, where it is depending what is the dimension it is having, how much the capacitor is there, the length, how much it is we are going to give for it, then where our capacitance is going to be placing, means about a permittivity of the homogeneous dielectric, the medium it is depending on. This is about the capacitance. Then how it is going to be measured? We know that it is measured by Faraday's. What is the Faraday is telling for us? It is of 1 coulomb of charge per 1 volt. Means for 1 volt, how many charges it is going to be occupying. That's what the meaning of the Faraday. And different values, what is going to be for the Faraday's units in terms of microfarad I can go, nanofarads, and also about the picofarads. Next, the same what is taken, we are going to applying for some of the medium here. Applying the definition of capacitance to a two conductors system in which the conductors are identical. Observe here, two conductors are identical and infinite parallel planes which is separated by a distance of d. It is shown in the figure. Observe here, this is two conductors, conductor surface here, then conductor face here, and uniform surface charge density, that is here in this case minus rho s, here it is plus rho s. The field what is going for E in the upward direction, and here z is going to be equals to d, and in this case it's going to be s0. Next, what is going for choosing the lower conducting plane, we were going to consider this at z is going to be equals to 0 and the upper is of z is equals to d. Then a uniform sheet of a surface charge, that is plus r minus rho s, on each conductor leads to a uniform field. On each conductor it is going to give a uniform field. Then E is going to be equals to rho s divided by epsilon into az, where permittivity of the homogeneous dielectric is of epsilon. Then I can write the equation as D is going to be equals to rho s into az. This epsilon, if I take here, epsilon into E is nothing but flux density only. That equation here it is writing. Then the charge on the lower plane must then be a positive. Since why it is going to be a positive, why it is showing here positive, since D is directed upwards and the normal value of D is going to be dn is going to be equals to, that is rho s. Then it is going to be equals to, here it is of z actually, is equals to the surface charge density. Then the upper plane is going to be dn is going to be equals to minus of dz, and the surface charge there is a negative of the on the lower plane. The surface charge it is having, it is of the negative value. Then the potential difference between the lower and upper planes is going to be taken as V0 is going to be equals to minus upper to the lower E dot dl is going to be equals to, substitute for E here, minus of d to 0. Here it is of d to 0 rho s divided by epsilon into dz, that is nothing but rho s divided by epsilon times d. If after integration you will be getting. So based on this, we can tell that since the total charge on either plane is an infinity, then it is in theoretical way. If I am going a practical approach, practical answer is obtained by considering the planes of each area is of S, whose linear dimensions are much greater than their separation what is going to be taken is of a D. Then the electric field and the charge distribution are then almost a uniform at the all the points are not adjacent to the edges. And if I'm going to take the edges points, it's not going to be considering here. Then, and this later region contributes a small percentage of a total capacitance, that is Q is going to be equals to rho s of that surface, that is nothing but V naught is going to be equals to rho s divided by F long into D, that is nothing but we can write there. Now the capacitance as C is going to be equals to Q divided by V naught, that is going to be equals to Q is of F long times R S divided by D. This is the capacitance value in a practical approach. Previously it is the equation what it is taken. This is in the theoretical we are telling. In a practical approach it depends on the surface area and also dimension, what is the depth, the depth, how much the distance is separated by two connecting materials. That's the thing it depends on. Therefore the equation represents the capacitance of the portion of a infinite plane arrangement having the surface area of S. Then if more than two conductors are involved, what is the condition we taken? If it is of two conductors. If it is going for rather than two conductors are there, then what is the equation is going for? Then the total energy stored in the capacitor is going to be, a W is going to be 1 by 2 integration volume with respect to volume, that is F long times E square dV. Then go on substituting for F long times of E, then it will be getting the equation. The volume here is going to be changing with dz and ds, where surface is 0 to s and dz is for the separation between the conductors is of 0 to d. Then solving for based on this, you will be getting as 1 by 2 rho s square divided by F long sd, that is nothing but I can write the equation as 1 by 2 F long time s divided by d rho s square d square divided by F long square. You will be getting the equation. Therefore, in general, in terms of the capacitance, I can write the work function as WE is going to be equals to 1 by 2 capacitance V naught square, or else that is going to be equals to 1 by 2 Q into V, or else I can write here as 1 divided by 2 Q square divided by C. This is the work, total work what it is required for the capacitance. Then equation indicates that energy stored in the capacitor with a fixed potential difference across it increases. Observe here, the potential is going to be in the capacitor, energy stored in the capacitor with a fixed potential difference across it increases as the dielectric constant of the medium it is going on increasing. Means it depends on the where you are placing your capacitors. It depends on the medium. Dielectric is more, then the storing capacity is more. We can tell that. This is about a boundary conditions and also about the capacitance. Capacitance is also very important question. Minimum of 6 marks it will be asking for you. Hoping you understood the concepts what I inform you. Okay, we'll stop here. We'll continue in the next class.